chemistry students. We are here with the part 2 of the chapter 4 test hints, which I am taping in the presence of an empty room, so I'm hoping the chairs give me some good feedback here today. Trying to get this posted earlier on so that you have access to the test hints as you go through the chapter. Hopefully that will be helpful. As you know, we are doing the second half of chapter 4, where we're learning about quantum numbers and orbitals and electron configurations and all that stuff. So you're going back to the test hints for the whole chapter, and the second half of them, the second set of 25 questions, will be your hints for the test that we're going to take in this part. So, test hint number 1 says what each of the 4 quantum numbers shows. Now, we designate the quantum numbers with letters, and you've seen this in videos, but you should know the letters N, L, M, and S. Okay? Those are the letters we use to represent quantum numbers, and they do have numbers that go with them. You need to know the names of each of those. N is the principal quantum number. L is the orbital quantum number. It's also technically called the angular momentum quantum number, but we usually refer to it as orbital quantum number because it shows the shape of the orbitals. M is the magnetic quantum number. And S is the easiest one. It is the spin quantum number. I'm not writing quantum number up here, but you get the idea. So, principal, angular momentum or orbital, magnetic, and spin. And this question, the hint says what each of them shows. Now, the question is actually only going to be about one of these. So you need to know these names. This is going to be very helpful for your honors page because you're going to have to recreate this for me. You're going to have to show me that you know what the letter designation is for each quantum number, what the name is, and what it shows. So keep track of this stuff. The principal quantum number shows the overall size of the atom and the energy levels. So it might be easier to remember it as energy levels. Size may also be helpful. Orbital shows the shape of the orbitals. Shape. And we know that there are 4 possible shapes: S, P, D, and F. And we'll get into a little bit more on those in just a second. The magnetic quantum number shows the orientation in space around the XYZ axis. And the spin quantum number, again, it's the easiest one, shows the spin. The electrons are either spinning clockwise or counterclockwise. Okay? And we've designated that with arrows, up arrows and down arrows to show one direction or the other. So the question in number 1 will be about one of these. Say, what does the orbital quantum number show? Well, it shows the shape of the orbital. The shapes are S, P, D, F. Test hint number 2 is just how to define quantum numbers in general. What are they in general? Okay, and this is a set of numbers that indicates the properties of the atomic orbitals. Okay, not just the atom, but those probable areas within the electron cloud where the electrons tend to hang out. That's the definition of an orbital, and you may remember seeing these models in the classroom and in some of the other videos. This is a model of one of the d orbitals, but there are various general regions where the electrons tend to be. All of our analogies have been describing them as if they were actual physical structures, and they are definitely not. They're just a probable location. But our analogies, to make them understandable, I think at this introductory chemistry level, it's often easier just to consider them to be kind of like rooms, little areas where the electrons are going to go. All right, test hint number 3 says which quantum number shows the number of sublevels within each energy level. Okay, we have these 4 quantum numbers, and the sublevels are this SPDF, the SPDF sublevels. And we know that there are 4 different sublevels. At the S sublevel, there happens to be one shape, and it is a sphere. At the P sublevel, There are 3 of those, and they are what we refer to as peanut-shaped. They're actually technical names that go with these, but they kind of look like peanuts, so we call them peanut-shaped. Your book might call them dumbbell-shaped. The d orbitals, there are 5 of those, and those are double peanut. And the f orbitals, there are 7, and we refer to them as flower-shaped. The real designations are spherical, principal, diffuse, and fundamental. But let's face it, who's going to remember that? So, in an introductory chemistry class, let's go with what we know and use a mnemonic device. Sphere, peanut, double peanut, and flower. Okay? Now, those, getting back to the test hint, those are the sublevels. Each energy level can have certain shapes. As you've been reading your electron configurations left and right across the periodic table, you know we colored in the S block for the first 2 columns, the P block over here in the upper right corner, the D block with the transition metals in the middle, and the F block with the lanthanide and actinide series down at the bottom of the periodic table. S, P, D, F are the sublevels. The question is asking us about how many different kinds there can be. In the first energy level, there's only one kind. There's only s orbitals close to that nucleus. In the second energy level, there are 2 kinds, s's and p's. Now, we know that there are 3 p orbitals, but there are 2 kinds. So you got to watch really closely on this test to figure out, is the question asking me about what kind they are, or how many of that kind there are. The d orbitals, or excuse me, the third energy level, we can have room for s, p, and d sublevels because we had that orbital overlap happening when we went from 4s to 3d. Our whole d block is kind of like it slid down a row on the periodic table. And that 4s snuck in and filled its energy level, or it filled its orbital before the third energy level was finished with the 3d. And then the f, in the f block, that starts at energy level 6 and 7, but it's really, or it's in row 6 and 7, it's really energy level 4 and 5, the 4f and the 5f. The third energy level can have s, p, and d shapes. The fourth energy level has 4, s, p, d, f. So it's easy. Level 1 has 1, 2 has 2, 3 has 3, 4 has 4. If there were enough atoms discovered or created to need an orbital beyond the f sublevel, maybe we need a few more rows on the periodic table, well then the 5th energy level could have 5, the 6th could have 6, the 7th could have 7, and so on. We just haven't created that many atoms yet to need that many electrons. Moving on to test hint number 4, how spin affects the electrons and how it allows 2 electrons to be close together. Okay, when we go to the spin quantum number, we know from properties and energy and magnetic fields that the electrons must be spinning. Electrons are negatively charged. All electrons are alike, they're all negatively charged. But if one spins clockwise and one spins counterclockwise, they create a magnetic field. And there's a little bit of magnetic attraction that actually holds 2 electrons together in this teeny-tiny little space of the orbital. Okay, atoms aren't very big, and when you consider that there can be all these different kinds of orbitals in them as well, you're getting electrons really close together, and they would rather repel each other because of their charge, but when they're spinning in opposite directions, then they create that magnetic field and they're attracted magnetically. So that's how spin affects the electrons, and the magnetic attraction is why they can be together. Test hint number 5. How energy at one level relates to energy at another level. All right,